So Google and DeepMind drop another AI bomb, and you need to see this. Real fast, just ask yourself, when are you going to have a robot butler that takes care of all your tasks around the house? Makes you coffee, cleans up after you, puts away the laundry, etc. It's not specialized in just a few tasks. I mean general purpose, like ChatGPT, but for dishes. So just think of a number. Is it 10 years? Is it more than that? Is it less? Where do you think we are? At what point a decent percent of the population is going to have a robot in their house like that? So there's this like repeating pattern in tech that software progress tends to move much, much faster than hardware. There's this famous quote, we wanted flying cars, but we got 140 characters, is a testament to that. We imagine the future as being full of robots and spaceships and flying cars. Instead, we get online shopping and social media and those weird TikTok videos where people eat the ice cream and say, thank you. What is that? But the same thing is happening with AI, it seems. We thought we would see this rapid rise of robots and automation, but large language models like ChatGPT are suggesting that we might see machine superintelligence before we can figure out how to make it walk right. It might be possible that humans never figure out how to make autonomous robot butlers. Before you panic, I mean that we aren't the ones that are going to figure it out. The AI will. So research out of DeepMind, NVIDIA, and OpenAI seems to suggest that training robots with AI and also within simulations seems to be much more effective than just trying to code something that's capable of interacting with the physical world. So for most of the computers that you and I interact with, most of the things we know about, they're coded by humans. A human wrote out line by line exactly what that thing should do. But recently we've seen this rise of AI, of neural nets. Now, they've been around for a while, but a lot of recent developments have really pushed the progress forward, and we're seeing it applied in more and more places. And they're beginning to solve a lot of problems that we as humans have struggled to solve ourselves. And this new thing out of Google DeepMind is going to show exactly what's possible if we rely more on the artificial intelligence than necessarily our own. Let's take a look. So this is the robot in question. This thing has been haunting various Google kitchens for, I think, a few years now. I think 17 months, they said. And there isn't just one. I think there's over a dozen of them running around. So this thing takes basic commands like, bring me a drink. And then it goes and it executes that command. The important thing to understand here is that nothing is scripted. It's not given a location of the object. There isn't some map that it can reference. It's that the AI is learning more and more about its environment and how to accomplish new tasks that it has not done before. So by now you're familiar with the term large language model, or LLM. It's like ChatGPT is the most famous one, but there are many others, including PaLM, which is Google's own LLM. So here, when they use the word language, just think of something like ChatGPT. It's a language model. It's something that can understand what you're saying, to reason about what you're saying, to prioritize certain tasks, something that can read some text and then make some insights or decisions about it. So that's language, aka large language models. Next, we have a high-capacity vision language model, VLMs, that are trained on the web-scale datasets, making these systems remarkably good at recognizing visual or language patterns and operating across different languages. So this is like ChatGPT with vision. It's able to see images and recognize them for what they are. By the way, we were supposed to get vision with GPT-4, and we're still waiting. I will need to speak with a manager about this. So VLMs are like ChatGPT. They can look at images and make sense of them. So anyway, so a VLM looks at images and makes sense of them. You can think of it as also being able to see the outside world as it's kind of moving around. It's able to see what's happening out there. If it looks on a bunch of objects scattered across a table, it can kind of make sense of which objects it's looking at. So, and then on top of this, we have this new thing. In our paper, and we're going to look at the paper in just a second, we introduced Robotic Transformer 2, RT2, no relation to R2D2, a novel vision language action model, so that's VLA, that learns from both web and robotics data and translates this knowledge into generalized instruction for robotic control while retaining web scale capabilities. That's the important part right there. Vision, VLA, vision language action model. So I think a lot of people believed in the past that Google's going to be the #1 manufacturer of robots at some point. That's where everything was going. I think this is showing that it's going to be a little bit different. More on that in just a second. So vision language action. So vision language is ChatGPT that's able to see. Now, obviously, of course, I'm saying ChatGPT because that's the thing that most people are familiar with. Google has their own version of that called PaLM. This is what they use here. But it's this last part, the action part, that's the new and exciting addition. So let's say you tell this thing to go get you an apple. It looks down, it sees an apple, and makes a plan. Pick up the apple and hand it to human, gently. Right? So all of that is the vision language part. Still learn about, but it's like a few months old at this point. In AI, I feel like if it's been a month, it's old news. But you get what I'm saying. ChatGPT with vision, we kind of understand what that is. But my point is that large language models with image recognition with that technology. But what's the next part? So the next part is the action of picking up that apple and how to move it. So the important thing here is you can think of it as several different models kind of working together, which is similar to what we're seeing with a lot of other research, like actually with 13 robots over 17 months in an office kitchen environment. So basically this announcement is of the RT2. So they use the RT1 robot. That's the thing that we saw probably in a lot of these images running around Google's kitchens and getting things for people and handing them. We'll improve that in just a second. So we showed that incorporating chain of thought reasoning allows RT2 to perform multi-stage semantic and energy drink. Now, I've been trying to convince Verinoas examples like this. Which object could be used as an improvised hammer? A rock. Are not great examples to use from a marketing standpoint. That makes my job harder. Think of things like plucking a flower to bring as a gift, for example. That would be much better. So this is the action part of it. To control a robot, it must be trained to output actions. We address this challenge by representing actions as tokens in a model's output, similar to language tokens, and describe actions as strings that can be processed by standard natural language tokenizers shown here. So we'll look at the paper in a second. One thing to understand is, for example, the reason that the large language models are able to be so effective at reasoning and at speaking is the way that they sort of save these tokens or words when it comes to large language models is that they kind of store them as clusters in relations to other words. So for example, a large language model might understand that things like cat, dog, pet, that there's some relationship between them. If you give it the words big and small, it's going to understand that there's some relationship to it. There's a great article called Large Language Models Explained with a Minimum of Math and Jargon. I'll link it down below. Really great if you want to have kind of a basic understanding of how these things work. But you can think of it as sort of understanding all these words with various clusters, and so it understands how they relate to each other. So for example, Google's word vectors capture a lot of relationships like Swiss is to Switzerland as Cambodian is to Cambodia, Paris is to France as Berlin is to Germany, mouse is to mice as dollar is to dollars. So my understanding, as far as I can tell, is this is something very similar. So just like we know that certain words have certain relationships, a lot of the movements that a robot can do is going to have some relationships. Picking up an orange and picking up an apple is similar to each other. There's going to be a lot of similarities. You know, picking something off a table that's 4 feet tall and a table that's 5 feet tall, that's going to have a lot of similarities. So by doing that, the AI is able to generalize a lot. Like if it sees a table, it doesn't have to be the exact same dimensions as all the other tables, etc. So what that means is each representation of an action that this robot can take becomes a string. A string is basically a sequence of characters. And so they're saying we use the same discretized version of robot actions as in RT1 and show that converting it to a string representation makes it possible to train VLM models on robotic data, as the input and output spaces of such models don't need to be changed. Now, you might be asking yourself, why is this thing working so hard on picking up a ketchup bottle? Those Boston Dynamics robots, they're doing backflips and dancing. This thing is dumb. Maybe Google should have kept Boston Dynamics instead of selling it to SoftBank. SoftBank, by the way, is notorious for losing billions of dollars on various high-tech investments, including WeWork, Uber, Fair.com, etc. Slack, those are some of the ones I know. And why did Google sell Boston Dynamics to SoftBank in 2017? They haven't sold any companies since 2012. They're not strapped for cash. So we're going to look at the paper in just a second, but I do want to kind of mention this. And what I'm going to say is pure conjecture. This is my guess. I don't know if any of this is true, but I think I have an idea of where Google is going with this. So Google sold Boston Dynamics in 2017. Now, 2017 is right around the time when that Attention is All You Need paper came out. And Google researchers were the ones behind it. And that was the paper that really moved the AI field forward, specifically the large language models. It addressed things like attention, transformers. It was a big breakthrough that allowed these large language models to kind of not forget what they're talking about. So they were able to coherently keep speaking and finishing their sentences. They call it attention. And that paper was probably a big part of why we're having this sort of massive LLM explosion right now. But my guess is that Google realized that, building robots is going to be hard, expensive, and it's going to be hard to scale globally. So I think they came up with an idea, and I think that's the idea that we're seeing here. So they wanted to design one AI model that was based on LLMs that will be able to hear any command in any language and then carry it out in any environment. And this is the important part, in any body, meaning like its physical body, what it looks like. Like if this thing looked humanoid, it would not have to have a brand new AI model control it. The same AI model could jump into you could take whatever this learned, plug it into a new body. It would have to relearn some of the skills, but the bulk of it is already in there. It's the large language model plus vision. So Google does not have to build physical robots. It can provide this as a service. Any company that wants to make robots or any manufacturing plant that's producing anything, whether they're in construction or military or elder care or manufacturing, whatever your robot looks like, you just plug and play into the Google AI system, and this will run it for some fee. It's robotics as a service. Meanwhile, each one of those robots will collect data and feed it back into Google, which is going to allow them to have more data, to have more improvements. The more robots they have, the faster they can improve them, etc. And each improvement that gets rolled out gets pushed out to all of the robots. So this means if Google has eventually, let's say, thousands of robots running around, all learning, collecting data, no one's ever going to be able to replicate that data without having a larger network, without somehow being able to launch even more robots that are running even longer to try to get more data, to try to improve on it faster. Keep in mind, data is like the most valuable thing when it comes to building the best and most futuristic, most advanced AI models. People that control unique data are likely going to be able to build unique AI models that no one else can replicate. Having a real world unique set of data gives you an unbeatable advantage. So I wouldn't be surprised if we're going to see these things pop up everywhere, but they're not necessarily going to look like this. The form factor, the physical appearance could be vastly different. It's going to have some grippers, it's going to have some claws or some hands, it's going to have an ability to see. It's going to have an ability to see and hear, and that's about it. But all that is ramblings of a madman, I'm sure. None of that is true, although it would explain a lot. So RT2's ability to transfer information to actions shows promise for robots to more rapidly adapt to novel situations and environments. In testing RT2, I keep wanting to say R2D2. In testing RT2 models in more than 6,000 robotic trials, the team found that RT2 functioned as well as our previous models RT1 on tasks in its training data, or seen tasks. And it almost doubled its performance on novel, unseen scenarios to 62% from RT1's 32%. That's the big thing right there. What that means is the more robots you have running around gathering data, the better they're getting, and also they're getting better faster. In other words, RT2 robots are able to learn things like we do, transferring learned concepts to new situations. RT2 shows that vision language models, VLMs, can be transformed into powerful vision language action models, which can directly control a robot by combining VLM pre-training with robotic data. It leads to significantly better generalization performance and emergent capabilities. RT2 is not only a simple and effective modification over existing VLM models, but also shows the promise of building a general-purpose physical robot that can reason, problem-solve, and interpret information for performing a diverse range of tasks in the real world. And I'm not going to go over it here because I already covered it so many times in previous videos, but there are many other examples of similar things like this happening, and people that are kind of like opening their minds up to this. So for example, Andrej Karpathy spoke briefly at an event, I think it was probably in the Bay Area in San Francisco somewhere, called AGI House. And he gave some tips for people that are trying to build autonomous AI agents. I have that video posted on this channel. I'll post it down below if you want to see it. But one of the things that was very interesting that he was saying is that, he's been doing this for a long, long time. And he was saying that a lot of things that they were doing with reinforcement learning and various autonomous driving vehicles that he was working on. He previously worked at Tesla. Now he's at OpenAI, of course. He was saying that a lot of it seemed, he didn't say it was wrong or it was a dead end. I forgot how he said it, but he basically said that might have been not the correct way to go. What he should have been doing this whole time is building large language models. And NVIDIA is doing the same thing by using GPT-4, a large language model, to create this autonomous agent that runs around Minecraft and is able to learn and code new abilities for itself. So basically what I'm saying is before I think we thought that each of these things is going to be like its own AI agent, its own AI model that is going to be unique and separate. And now more and more it's seeing like, no, you just take a large language model, this thing that is able to think, and you just plug it into something else that you want it to do, and then it just does that. And yeah, you have to give it some tools, you have to give it some training, you have to, let it figure out how to do stuff, but that's the brain. And we just got to figure out, okay, how do we hook up all the other things that we need to that brain, and then it can function. All right, so I'll leave these links below for those of you that want to read the full paper. Looks like they were pulling a lot of these like important things and just putting that in the blog post. The other thing that I'm not sure I mentioned, but Palm is one of the best large language models for being able to talk in different languages. Instead of being really good at one language like English and maybe not so good at the other ones, not only is it pretty good at all of them, like the spread isn't as big as some of the other LLMs where like English is number one and then it barely speaks some other language. This is a little bit better. It's more passable at more languages, but also it's able to just flip back and forth very easily. And I think that's going to be here because, think about the scale of launching something like this worldwide, having to go into, China versus the various European countries versus LATAM versus Africa. You don't want to be dealing with a lot of different languages and having to build out a team that speaks the languages, try and train them up so they can train the other people how to use the robots. No, it's all in one. You just speak to the robot in whatever language you're comfortable in. You're speaking in natural language. You tell it, go fetch me a drink, and it goes. If you need to adapt it to a factory, then you might have to, maybe explain in detail kind of what you want it to do. You pick up the doll head here and you put it on the body and then you put it back on a conveyor belt or whatever. But as soon as this is launched, as soon as this is like ready for showtime, and we have some sort of robots that are capable of running this, or maybe even like just these robots that we're seeing here, like there's no other friction in terms of how fast you can scale it globally. There's no language friction. There's no training friction necessarily because most of it, you're just going to talk to it. So I think when this launches, it could scale really fast. While a brute force approach might entail collecting millions of robotic interaction trials, the most capable language and vision language models are trained on billions of tokens and images on the web, an amount unlikely to be matched with robot data in the near future. Yeah, I mean, this is the big breakthrough that this thing has. We're really good at this. We're really good at the LLMs and vision, not so much at the actual robotic thing. So have the LLM handle more of the robotic interactions. To this end, we explore an approach that is both simple and surprisingly effective. And that is training the LLM models to create dialogue to output the low-level robotic actions. When Elon Musk was talking on Twitter Spaces about launching the xAI, his new AI company, he briefly mentioned that there were a lot of things that people were doing on their way to AI and AGI that based on new knowledge, it seems like it will be a lot simpler than a lot of people thought. And he didn't explain what he meant by that. It was kind of cryptic, but I wouldn't be surprised if he's kind of referencing the same exact thing. If he's saying that a lot of this is just sticking LLMs as pilots in various things and making it work. For people that are returning to my channel, I think I bring up this study like a couple of times per video, Voyager, the Minecraft AI, and I apologize if you've seen this before, but I feel like this is going to be the core to a lot of different things. So here they use GPT-4 as a reasoning engine to make a lot of decisions about how to do stuff. And they use another instance of GPT-4, again, to write code and test the code here being little skills that you can use in Minecraft. And the results are incredible. This thing continues to learn, continues to improve, and just keeps going. By the way, this person here, I believe Lingxi Fan, that's Dr. Jim Fan on Twitter. A great follow if you're interested in all of this stuff. That's his project among everybody else, of course, on here. But he was the one that actually alerted me to this thing. Internet scale text, image, and video data can be used to help the robot develop better common sense. No special architecture means the model isn't restricted to specifically formatted robot-controlled data. The full firepower of prompt engineering is now unlocked. Chain of thought, vector DB, no gradient architectures, you name it. The simplest approach almost always performs the best in modern AI. Anyways, great person to follow, well-known in space. I believe he worked with Andrej Karpathy, and I'm excited where they're going to take things next. Very exciting. So this is interesting. So one of these, so for the people that are listening right now, there's an image of this robot completing some tasks. And one of them has a bunch of flags on the table. There's the German flag, the American flag. And so the prompt on one of them says, move banana to Germany. And so the robot, moves the banana to Germany, or on top of the German flag, rather. Then another one says, put strawberry into the correct bowl. And there's several bowls, some with, apples it looks like, some with berries. So he puts it in the correct bowl. And there's a bunch of toys on the table. It says pick robot. He picks up the robot toy amongst various other toys. It is very simple because this is something that's pretty obvious for large language models. And this was something that was incredibly difficult to do with robotics. I've been following the space for decades. I know some people that are researching some of this stuff. And I mean, it didn't seem like there was too much momentum. I mean, it always seemed like, there was always progress and always improvement, but it was kind of like incremental and it was kind of crawling along. Now it almost seems like we had this breakthrough with LLMs and now it's just diffusing across everything and making everything a little bit better. On this page of the paper, they're showing how the RT1 performed versus the RT2. And they're using two different LLMs. So Palm E, 12 billion parameters, shown here in green. And there's another one, which is the RT2 robot with the PAL E X 55 billion parameter model. And this is showing that almost doubling of how well it does. Once they took all the data from RT1, they fed it back into the RT2, and they're testing it, how well it performs with tasks it's seen before. So if you ask it to pick up an apple, how well does it perform at picking up an apple? Then they're testing it with unseen objects, meaning new objects, unseen backgrounds, unseen environments. And on average, we're seeing that, yeah, those things do about double. I believe they said from 32% to 62 or something like that. But it's a near doubling of its performance on unseen novel tasks, which is the big metric here. If it's able to just figure out how to do stuff that's never done before, on first glance, that would make it extremely, extremely valuable. Then they briefly mentioned some limitations of this program. So I'm basically saying while it's able to pick up a lot of new skills, one thing that doesn't seem to be able to acquire right now is performing new motions. So various motions that it can do with its hand, it doesn't pick up on how to do new motions. An exciting direction for future work is to study how this could be acquired with, for example, videos of humans. So it watches, 1 billion hours of humans picking stuff up, and it's like, oh, you can move your elbow this way or whatever. Another thing they mentioned, of course, that running this in real time is the computational cost is very high, but in the future, they're hoping that if they're able to explore quantization and distillation techniques, they might be able to run it at higher rates or lower cost hardware. I mean, with the way things are progressing, I think that the price to run stuff like this will keep dropping. And if you think about how valuable something like this would be, I mean, would this be more valuable than Google right now is worth, than most tech companies are right now? I mean, if these are able to completely automate all human labor, not only that, but scale it infinitely because we can just create more of these. I think Elon was talking about that, saying that his bot, if it's released, could be worth more than full self-driving cars or worth more than Tesla is. I think his point was they would completely change the GDP calculation, how we calculate the output of a country. But I'm going to wrap it up right there. The last thing I do want to mention, that one thing they didn't talk about here is that NVIDIA and DeepMind itself, in fact, they're utilizing simulations to teach these robots how to do stuff. So instead of training them in real time, so for example, with the R2D2 or whatever, RT2, that was trained in real time. So it walked around, picked this thing up, and that was one piece of data. One thing that NVIDIA and OpenAI and DeepMind themselves have done is they would train some of these robots in a simulation where time could obviously run a lot faster. So they can, train 42 years in a span of minutes, for example. I think that was one of the numbers that I heard with NVIDIA. And that has yielded some very interesting, very good results because these robots, you drop them in there, short time passes here, on Earth or whatever. And when they come out, they're ready to go and they're very effective and they have all these moves that they've learned. And then you take that, you plug it into their physical robot body, and it tends to work pretty well. One thing, since the real world is a little bit more chaotic, there might be little variations here and there. Like, for example, even if you think about something like electrical currents, right? In a simulation, if you just set it to be the same all the time, that might be different from how the real world is. Maybe there's some low connection that's misfiring. Maybe the circuit's a little better, the battery's a little low. Maybe there's some wind, maybe there's some friction, etc. But they're even getting around that by randomizing a lot of the factors in a simulation. So what they're seeing with that is these robots are coming out more robust. They're even better able to handle real world conditions because of those random factors that they witnessed in the simulation, which wasn't that the whole thing in Dragon Ball Z, that hyperbolic time chamber, that they would go in this hyperbolic time chamber and they would train there for 100 years and only a day would pass. And then they would come out and be these super strong people. I mean, Dragon Ball, that was in the 90s. They figured this out in the 90s. Anyways, thank you for watching. I'll talk to you next time. My name is Wes Ralph. Subscribe.